3 is based on the algorithms. So we'll get the opportunity to look at 4 different algorithms and then examples that go along with the algorithms. They're all based on the recursive formula. So I'm hoping that this is gonna be very helpful for the remaining of the examples that were planned to be completed on Thursday. We did not get that time to complete it on Thursday. So let me go ahead and then share. These are additional notes that you can find in Brightspace under the module lecture notes. And these are specifically the final lecture notes, additional lecture notes of chapter 5. So recursive formula and algorithms. We did examples of the recursive formula directly related to sequences and the terms of the sequence, including applications of the recursive formula, and some of them expanded to a well-known method in mathematics, such as the mathematical induction. Now, the work that we looked at the recursive formula now will be expanded into with a goal to find the preceding term based on the previous term, but will be extended into formulas that are related to functions and their algorithm operators. So the first example that we study and the first algorithm will be the algorithm of a function known as a factorial function. So factorial function is based on definition of, in general, factorial notation. The factorial function has a typical structure that is based on the recursive formula, but at the same time based on the definition of the factorial notation. So a function f of n is not defined as a factorial function in the form of a piecewise defined function if for n equals to 1, this is known as the initial condition, is equal to 1, and then for all the other n's that are greater than 1, based on the recursive rule, f of n, which represents the preceding term, will be computed by n times f of n minus 1. So in order to understand the piecewise defined recursive formula of the factorial function, let's look at an example of using this formula to compute 5 factorial. So let's say n is 5, and then we're trying to compute in the form of a factorial function f of 5. So if I look at the way function is defined, if n is 1, this is the initial condition, then f of 1 is going to be 1. But if n is greater than 1, then we have to use the recursive rule. So let's transition into n equals 2. So f of 2, which represents f of n, we look at this as n, in this case n is 2, times f of n minus 1. F of n minus 1 is going to be f of 2 minus 1. So this is a product of 2 times f of 1. Now from the previous term, or obviously from the initial condition, f of 1 is 1. So that's going to be 2 times 1, which is 2. Now we'll transition into f of 3, n in this case is 3. So this is going to be the product of n, which is 3, times f of n minus 1, which is f of 2. So this is 3 times 2. The value of f of 2 from the previous step is 2. So that's 6. Now this particular term, f of 3, will be used in using the recursive idea or the recursive rule to get f of 4. So f of 4 is going to be 4. That represents the value of n times f of 3. So that's 4 times 6, which is 24. And finally, this is what we are looking for. Remember, f of 5 is indeed the 5 factorial, is 5. That's the value of n times the value of the previous term, which is f of 4. So 5 times 24, 120. And that is indeed the value of 5 factorial, so represented by, in the form of a piecewise function known as the factorial function, f of 5 is 120. So in the form of an algorithm code, this is going to look like, based on what we did, it's going to look like, it is known as a factorial algorithm, and then it is defined by function factorial. then n, which is an integer. If n is equal to 1, then return 1, else return n multiplied by factorial of n minus 1, which is the function factorial of n minus 1. So if I have to use the algorithm, how this is going to look like? Trace the algorithm factorial 5 using the factorial algorithm code, which is given above. Now, reminding everyone, there's no need to memorize the algorithm. They're going to be part of the directions when you take the quiz or any other assignments that uses the algorithm codes. So let's start with, so the first column of this table represents the values of n from 1 to 5. The second column, we compare n to 1, and then we are going to respond yes or no based on if n is equal to 1 or not. And then we'll apply the formula. If n is not 1, then we're going to multiply the value of n itself by the factorial of n minus 1. So using the algorithm code. So let's start with the initial condition. N is 1. N is obviously equals to 1. So that's a yes. So factorial of 1 is 1. Because based on the coding, if n is 1, then return 1. Now, if n is 2, 2 obviously is not the same as 1, so the answer is no. So therefore, factorial of 2, based on the coding, will be computed as the value of n, which is 2, times the factorial of the previous term, which is the factorial of 1, and that is 1. So that is 2 times 1 equals 2. Now let's look at 3. Factorial 3, 3 compared to 1, they're not equal, so the answer is no. Factorial of 3, then, based on the coding, is going to be the number 3, which is the value of n, times factorial of 2. So that's 3 times 2, which is 6. We follow in the same way, in a very similar way, to get factorial 5, obviously, as 5 times factorial 4, and that's 5 times 24, 120. So if you look at the table, that is pretty much well designed, the same as the factorial function, which is given in the form of a piecewise defined function. So the algorithm code almost works the same. Now, using the same idea, the second function that we introduced is the exponential function. Now, the exponential function is equal to, is defined by a formula that is, again, a recursive formula, but the function recursive formula that is defined in the form of a piecewise function. If n is equals to 0, so remember n is the exponent of the exponential function, then f of n equals 1. So in other words, if you have a finite base raised to the 0 power, the answer is 1. This is known as the initial condition. But if n is greater than 0, then this is going to be a, which is the base of the exponential function, times f of n minus 1. So this comes from the idea, if I have base a raised to the power n, this is going to be a times a to the power n minus 1. Where this idea comes from, if you multiply powers of the same base, you add exponent. Now, a by itself is a to the power 1. So a to the power 1 times a to the power n minus 1, you add exponent. So you have a to the power n minus 1 plus 1. 1 cancels out, so it's a to the power n. The same idea is used to create the piecewise defined function known as the exponential piecewise defined function. So now let's transition to this is the recursive formula. So let's look at one example. So we are going to trace the algorithm. The exponential algorithm is function exponential. AI is the positive integer. This positive integer must be different from 1. This represents A represents the base of the power, and then n is a non-negative integer representing when we say non-negative, this is 0 and positive. So anytime we use the term non-negative, it's not the same as saying positive integer, because positive integer 0 is not included, non-negative integer 0 is included. So n is non-negative, meaning not only positive integers, but 0. So n equals 0, and then n greater than 0. And then that's important because these are the two conditions of n, exponent n. n0 is used for the initial condition, and then n greater than 0 for all the other exponents. If n is equal to 0, so exponent is identically 0, then return 1. Else, return a times exponent of a n minus 1, which is a to the power n minus 1. We're going to come back to the greatest common divisor later on. For now, you just ignore this initial. And now let's trace the algorithm exponent 3, 4 using the above code. So the first column of the table represents the value of n starting at 0 going all the way to 4. Now the second number of this order pair is the exponent, is the value of n, and the first number is the base of it, which is a. So the notation is exponent a comma n, which means a to the power n. Now if n is identically 0, that's the column that we are comparing n to 0. We're going to say yes, otherwise no. If it is a yes, that's automatically initial condition, which is the same as 3 to the 0 power 1. Else, we are going to multiply the base 3 by the previous term, the exponential of the previous term. So let's start with 0. 0 is indeed identical to 0, so that's a yes. So therefore, 3 to the power 0, which is exponential of 3 comma 0, that's another way of writing this function, that's 1. This is the initial condition. Now let's get to n1. We know n is not 0, so that's a no. Therefore, 3 to the power 1, the first number of this order pair, right after the word exponential is the base, and then the second number is the exponent. So exponential 3, 1, which means 3 to the power 1, based on the algorithm coding, is going to be equal to the base, which is 3, times the exponential of the previous term. And the previous term is 3 comma 0, which is 3 to the power 0. So that's 3 times 1 equals 3. Following in a very similar way, we can look at the largest exponent for this example. Remember, we are tracing the algorithm of 3 to the power 4, which is exponential of base 3 and exponent 4. We know that n is 4, that's exponent. 4 is not 0, so the answer is no. Therefore, exponential of base 3 and exponent 4, it's going to be 3 times the previous term, which is the exponential of 3, base 3 exponent 3. And the exponential of base 3 exponent 3 is 27. So that's going to be 3 times 27, which is 81. Now, this is the second application with an algorithm code known as the application of the exponential algorithm. And the function, again, is given as a piecewise defined function known as the exponential function. Now we'll transition into the very first algorithm that was discovered during the area of Euclidean. The Euclidean area, in addition to other work that was done in the area of mathematics and geometry, Euclid was well known for discovering the first algorithm in the history of algorithms, and that's the foundation of what came later on as the algorithm coding that became the foundation of the computer programming. The algorithm that Euclidean created, known as the Euclidean algorithm, it is based on GCD, known as the greatest common divisor. Euclidean and used the recursive idea to compute the greatest common divisor, GCD, of A and B. So what is the greatest common divisor of A and B? Now we need to know what is A and what is B. A is the dividend, B is the divisor. So by finding the greatest common divisor between a dividend and divisor, Euclidean created for the first time not only the first algorithm code, but the foundation of what was known later on as the algorithm of the long division, or the well-known the log division algorithm. We have studied the long division algorithm. In this case, A is the dividend, B is the divisor, Q is the quotient, R is the remainder. Now, Euclidean proved that the greatest common divisor between dividend A and divisor B is the greatest common divisor between the divisor B and the remainder. And this was one of the major discovery in the area of mathematics, and especially in the field of long division and then synthetic division later on, and polynomials that rely a lot on long division and synthetic division, which transition into solving polynomial equations. So what Euclidean was saying, the greatest common divisor of A and B is A mod is A is the greatest common divisor of B, which is the divisor B, and A mod B, because A mod B is nothing but the remainder of A divided by B. Let's try to see this in an example setting. So this is the Euclidean division algorithm code. So you find the GCD, which is the greatest common divisor between A and B. Both A and B are positive integers. A must be greater than or equal to B, otherwise the division is not possible. Remember, A is the dividend, B is the divisor, so you cannot divide if B is, you get the quotient 0 if B is bigger than A. So it is required that A is greater than or equal to B. Now, if B is automatically 0, then you return A. But else, the greatest common divisor is going to be equal to, else you return the greatest common divisor between B and the remainder. Reminding everyone the remainder R is nothing but A mod B. So if you divide A by the divisor B, the remainder of this division is R. So let's try to use this algorithm in an example setting for a better understanding. So trace the greatest common divisor Euclidean algorithm for the numbers 120 and 25 using the code above. So we identify A, the dividend, to be 120, and the divisor B to be 25. So the first two columns are the values of A and B. Then we have B compared to 0, because this is where we get the initial condition. If that's going to be no, then we have A mod B. So we literally dividing A by B and then considering the remainder, which we are going to specifically say for A 120 and B 25. And then from there transition into the greatest common divisor between them, because we know that the greatest common divisor between A and B, according to the Euclidean algorithm, is nothing but the greatest common divisor between B and R, between B and R. So what we do in this case, we start with the value 120, and then we divide 120 by the divisor 25. After dividing 120 by the divisor 25, we get 25. So let's look at the numbers. I have the numbers below. So if we divide A 120 by 25, we get 25 goes to 120 4 times. 4 times 25 is 100. So therefore, the remainder is 20. So I'm going to go ahead and then write 120 mod 25 is 20. So now I'm looking at the greatest common divisor between B, which is 25, and then A mod B, which is the remainder, that's 20. And then we'll transition into the next step. So now A becomes 25, and then B becomes 20. These are the two new numbers. Is 20 equals to 0? The answer is no. So now we divide 25 by 20, and then we look at the remainder. So if A becomes 25, B becomes 20. So here's the algorithm. A divided by B, we need to get the quotient Q plus the remainder. So 25 is A divided by 20. 20 goes to 25 one time, and the remainder is 5. So therefore, we have B is 20, and the remainder is 5. Because it's greatest common divisor between B, which is 20, and then the remainder of division between A and B. So the two new numbers for A and B are 20 and 5. So I'm going to write 20 for A and then 5 for B. And then 5 is not 0. So then we divide 20 by 5. So A 20, B is 5. So how many times 5 goes to 20? 4 times. The remainder automatically becomes 0. So we are getting close to finalize this, because remember, the coding is saying if B automatically becomes 0, remember, anytime you get the remainder, this is the new value of B when you transition into the next step, then you return automatically A according to coding. So if you pay attention, any number that we generated as a remainder becomes the new B, right? So the first remainder is 20. So this was the new B in the next step. So we got the remainder 0. So that means A is 5 and B is 0. If B is 0, 0 equals to 0, that's a yes. So therefore, you return A. So the greatest common divisor between 5 and 0 is indeed A, which is 5. And that's going to be your final solution. Remember how we started? We were looking for the greatest common divisor between 120 and 25, and this is nothing but 5. And now the last algorithm is the merge sort algorithm. The algorithm allows you to have a list of numbers and do two major steps. Using the algorithm, you split the list in two equal parts, and then after splitting, you merge and sort at the same time. So you can go back to a long list of numbers that are not only together as one list, but they're sorted out. So we are going to, this algorithm is a little bit more complicated than the previous one. Again, we rely more on the practical side of it, but let's go over the algorithm just to get a feeling how the algorithm is going to look like. So the procedure is merging and sorting. So you have a list of numbers that we call it E1, E2, E3, all the way to En. So these are n entries. If n is greater than 1, list is already sorted, then all you have to do is split the list into equal parts. So you are going to find the middle. Now be very careful. If this is a set of even numbers, then it's easy to split it up. Each one of them is going to be, let's say, 10, 5, and 5. But if it is odd, you get the number in the middle that goes to the left-hand side of the first half of the list. So joins the first half. And you're going to see that while I'm sorting, splitting, and then at the same time merging back into just one list. So you're creating two new ones. We call them L1 and L2. And then once you create two new ones, then you merge them back. But the process of merging back in one list requires sorting them at the same time. So let's try to perform the merge sort algorithm for this particular list that is below. The numbers are 5, 10, 7, 1, 9, 16, 8, 2, 4, 13. So we're going to split part 1 in two halves, and then we're going to merge and sort. So we can go back. When we go back, one list, that's going to be sorted out. The one that we have is not sorted out. So let me start off by counting. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So an even number of elements in this data set. So we're going to split it up in two equal parts, which means 10 divided by 2, 5, and 5. So notice that the first 5 are 5, 10, 7, 1, 9. And the last 5 are 16, 8, 2, 4, 13. So the first split into equal halves. The first half to the left includes numbers 5, 10, 7, 1, 9. And then the first half to the right, 16, 8, 2, 4, 13. We're not finished. We're going to continue to split again. Remember, anytime you have an even number, then you do equal. The first numbers that are not sorted are going to create the first half, and then the same group is going to create the second half. So the split is equally the same. Now, if you have an odd number of elements in the data set, when you're splitting, you get the number in the middle, but the number in the middle joins the first half. So I have a 5 number. I have a data set that is not sorted, a list of numbers with 5 entries. Then obviously 7 is right in the middle. 7 is going to go along with the first half, which is 5, 10. So 5, 10, 7. And then 1 and 9 together. We follow the same procedure with the other one. 2 is in the middle. So 16, 8, 2 all together, and 4 and 13 is the other half. Now, if we look at 5, 10, 7, that's still the first half that we just generated from the previous step has an odd number of entries in there. So we go in the middle. The middle is 10, which is going to go with the first half. So that's going to be 5 and 10. 7 stays alone. And then, of course, 1 and 9, it's 2 entries in there. An even number of elements splits into equal parts, 1 and 9. And now, finally, we have to do the same thing for the remaining 16, 8, and 2 in a very similar way. 3 numbers, an odd number of entries in there. So 16 and 8 together, the first or the left half, and number 2, the other right half. And then 4 and 13 splits equally the same, 2 entries, an even number of entries in there. So 4 and 13. And then in the final step, we have 2 completed, 4 completed, 13 completed, 7, 1, and 9. They're all completed. They're individual numbers that are created by splitting in halves in this continuous process. Now we have to split in halves the remaining portion, 5 and 10, and 16 and 8. So the final numbers are 5, 10 separated, and 16 and 8 separated. Now let's get this together in one list, but as we get them together, we have to sort them out. So these are the numbers that we generated after splitting up: 5 and 10, 7, 1 and 9, 16 and 8, 2, 4 and 13. How do I merge them? As we merge, we need to sort them out as well in order from the smallest to the highest. So I start with 5 and 10. I merge them in 1. So they're separated. Now we're merging them next to each other, separated by a comma. So now we have 5 and 10. They're in order. So 5 is smaller than 10, so we leave them alone. I'm going to drop down 7. And then 1 and 9 merge in one set. 1 and 9 separated by a comma. Now when we get to the other half, we have 16 and 8. If I merge them in 1, then I have to swap them. So 8 is going to come first, then 16. We bring down 2, which is alone, and 4 and 13 are going to be just merged together, no changes. Now let's do the next merging. We see an individual number, so we are going to merge together 5, 10, and 7. As we merge them, 5 is going to stay as it is, but 7 is going to be swapped with 10. So 5, 7, 10, and 1 and 9 continues to stay the same. So notice the branches of the 3 as we transition to the final step. Same thing, 18, 16, and 2 together, merged. By 2 is the smallest. So this group of 8 and 16 will be swapped with number 2. So we have 2, 8, 16. Continue to keep 4 and 13 as they are. And now the final merge, where 5, 7, 10, and 1 and 9 will be merged all together. We know 1 is the smallest, 5 is the next smallest, 7, then 9, and 10. So as we merge them in one list, which is the first half, we sort them out in the ascending order from the smallest to the highest. Same thing with 2, 8, 16, 4, and 13. We start with 2, then 4, then 8, then 13, and 16. Now we have the first half of 5 entries and then the second half of 5 entries. We're going to merge them in one list. As we do, we are going to sort them out as well. So we start with 1, which is the first element, and then merge 2, and then merge 4, then merge 5, merge 7, then 8, merge 9, then 10. So both are as part of the first half, then merge 13, and then 16. And that's going to finalize the process of merge sort, which requires splitting in half and then merging them back. But as we merge them, we sort them in the ascending order from the smallest to the highest. Thank you for watching.